present you this talk about writing Linux schedulers in Java, and we'll start with the problem motivation. Because if you're like Johannes and want to bake bagels and make chocolate QR codes and bake Franzbrötchen all at the same time, both the oven and Johannes can't do multiple things at the same time. So you'll have to somehow schedule them. And yeah, that's why we need schedulers. And we also need them on our computers.
And so the idea is here that we have essentially multiple tasks here, as David already said. We have cooking, we have chocolate molten, everything, and we have multiple CPUs. But I think we can simplify this, of course, to a 2 CPU setting. And what's like the simplest solution for this problem of scheduling?
Just run one task and abandon the second.
But that would essentially mean that I would only focus on chocolate QR codes. This would be nice, but the breakfast would be slightly more empty. So another approach is here. We schedule task 1, then task 2, then task 1. If you're wondering, task and process is essentially the same for our terminals here, because in the Linux world, we essentially have processes and like threads, and they are similar. The main difference is that they share an address space or not. But yeah, you can ignore it here. And so we schedule this, and this kind of works. So, but here the sound that we need to start playing. We have sound. Could we play sound, dear people? Oh, ich brauche Musikklinke, danke. Okay. Entschuldigung. Auf welche Seite? Do you hear the sound? It changes. When we play a game, it changes too. The magical sound is the magical sound of your system. But what is the sound?
It's the sound of scheduling. Like the talk topic might have revealed. Yeah.
So it's essentially a scheduler that we wrote. Because, of course, in Java. Because that's what we all need. We like Java. I'm not only saying this because I'm a JDK developer. Anyway. But why would we do this? Why would we write such a thing like a Linux scheduler that runs in kernel in Java?
I think the better question is, why not? As Clarke's second law states, the only way of discovering the limits of the possible is to venture a little way past them. And apparently, sound-producing schedulers are within the possible.
And we're seeing later that we can do even weirder things. Anyway, I have here this box and the tuning fork with me. I hope you can scream loudly. But I don't want to tell you too much about talk. But how could we usually modify the kernel?
So to modify the kernel, especially to add a new scheduler, we either have to change the whole kernel and compile our own Linux kernel, or we would have to add a custom kernel module, but with schedulers, this is currently not even possible at all. And both these ways are not the nicest to use and not the easiest to maintain and whatever.
And the problem here is that currently we only have a few schedulers implemented in your system. We currently usually use one scheduler, like the eBPF scheduler, which is the scheduler that came in after CFS. And why is this a problem?
Because we might have very specialized applications we want to write very specialized schedulers for that might be especially efficient with these schedulers. Or we might want schedulers that play sound.
Of course we want. So let's create our own. Has someone in this room, except us both, done this before? Who of you has written their own scheduler before? Okay. Cool. That's more. And only one of them is a PhD in operating systems. Cool. I spotted you. Anyway, if you're not a PhD in operating systems, you probably didn't write a kernel module or recompile a kernel because, well, it's a GPN, so it's probably likely that you already did. Hi, dear Gentoo users. But how hard could it be for all the other people there? How hard could it be?
I mean, with SCADX, which we present, it's not hard at all. So with SCADX, it's a bit hard because it boils down to the hardest problem in computer science, naming your scheduler. But other than that, SCADX provides you with sane defaults, so you can just implement one function, and that's already a custom scheduler you wrote, so it's not hard at all.
And there's where eBPF comes in. SCADX are the kernel extensions, and we have stickers in the front point for the Linux kernel that allow you to use eBPF to write your own schedulers directly. To quote Brandon Craig, he's shouting at hard drives in a system. It makes sense if you go to the video link. eBPF is a crazy technology. It's like putting JavaScript into a Linux kernel. He didn't mean this as an insult. He meant this nicely. I don't know. I know I get this laughs every time. Should have done this at a JavaScript conference. Anyway, they'll probably laugh different. Anyway, that's how it looks like when he doesn't show that hard drives. And he is the inventor, for example, of rankdovs. So essentially, eBPF allows you to extend your Linux kernel, which is pretty cool. So what's the idea of eBPF?
So with eBPF, we start out with some source code, probably C, but since we have an LLVM backend, we can also use C++ or Rust, or probably other languages with an LLVM backend. And then we compile it to eBPF bytecode, so an ELF file in the specialized eBPF instruction language. And then we submit it to the kernel via the eBPF syscall.
And then we have a problem. We want to check that there aren't any problems in the code. Like, we don't want to have our code running in kernel, for example, segfault. That would be kind of disappointing. So we verified, and we also verify in this, like, not with formal proof, but like with program analysis, that it terminates. But of course, this is a problem. As any one of you who studied somewhere knows, that we can't really prove that the program terminates, but we can if you just restrict it to the number of steps that it can take. And that's a problem because if your program runs too large, if you write a too large program here, it never passes the verifier. But what we then do, if it's approved, we pass it through a JIT compiler. This is supported on all major platforms like S390, like it works on the IBM mainframes, yay. x86 on all the platforms that nobody uses, and then we attach it to system calls, to sockets, anywhere you can write firewalls, for example. And then we have eBPF maps. They essentially allow us to communicate between user space on the one hand and kernel space on the other hand. That's why when you hear the sound, this is actually a two-part system. Like we have the user space part that gets the data from the kernel part, and the user space part emits the sound, and the kernel part does the scheduling. And yeah, that's where SCADX comes in. Yay.
So yeah, SCADX is the specialized part of eBPF, which allows us to easily write custom schedulers. And yeah, that's one slide from one of the engineers of SCADX. Cute penguins are improved the slides. Yeah, and it allows for ease of experimentation and exploration, especially over the techniques we previously discussed, like if you have to recompile your kernel, your whole kernel, to make a slight change in your scheduler, and you'll have to reboot your system, and with SCADX you just terminate your program, run it again, and you have the new scheduler. It allows for easy customization and rapid scheduler deployments, which is also maybe, especially in data centers, a big advantage over rolling out a new kernel all over the whole data center.
And so we now come to the part which is essentially related to you. Maybe you heard it, or maybe you gave the lecture at uni, but it's about that you heard in operating systems course about what are our goals, and we'll call back on them and show you that these goals might be sometimes pointless. But anyway, one of the goals is fairness. We want everyone, every task to get a fair share, depending on the priorities. Then of course we want to utilize the resource, so if we just don't schedule any task, it's really fair. Nobody gets the CPU, yay, but it's also not really nice because we don't do anything. We're essentially only having the scheduler overhead, so the overhead needs to also be not that big, because if we're just scheduling all the time, it's really cool as schedule developer, but for you, well, maybe you can play games with a scheduler, but that's topic for another minute. Anyway, and we also want responsiveness, because when I move the cursor here, it should really move. I can tell you, that's kind of weird to show, because the last time we gave this talk, it was over Zoom. We presented from here to there via Zoom, and if you show responsiveness of schedulers and have Zoom in between, no. Anyway, this time we're doing this. So what we have here is an example application. I can really recommend it. It's really nice. It's a game that you can also find on Steam. And because we're here at GPN, we choose a bus, and yeah, doesn't have some engine noises. The cool thing is we use this to see the FPS here and see the responsiveness and see how it affects how different scheduling policies affect our different our writing mode. So yeah, now SCADX, Sonia already told you, David already told you, is essentially the ability to write your own schedulers with ease. And so now we create one, because that's why you might have been here. It's really simple in Java. Just extend the BPF program class, implement the scheduler interface, and you're done. Good. Should we go home? Maybe. Anyway, and this scheduler is really tiny. It's like 10 lines of Java code, 20 lines of Java code, and its performance is good. In some benchmarks, it even is better than eBPF, which is kind of weird, because it's the simple scheduler. It's just like, oh, task, you want to go in the CPU, have the CPU for 10 milliseconds, that's fine. But how does it work?
So to write our schedulers in Java code, we of course implement the scheduler interface, as Johannes just showed, and then hello eBPF, the eBPF library Johannes created, transpiles your Java code with a compiler plugin to C code, and then we just hand the C code off to Clang, and Clang then compiles it to the bytecode ELF file, which is then loaded into the kernel, as we previously showed, and then just uses the SCADX eBPF interface to implement the scheduler.
So let's see some schedulers. I think that's the interesting part. With every of these schedulers, we first give you an impression what it does, and then show you how it's implemented and how it affected. And this will be like the major part of this talk here. There's the most simple scheduler is the first come first served scheduler. It's essentially, it tells the process, hey, run as long as you want. We won't stop you. It's like telling me, like, you can have the oven for baking bagels as long as you want. Who cares about pizza? It was actually kind of true. Like, I was finishing the bagels, and someone from the kitchen team was like, how long do you need the oven? I'm like, There's only like a few plates of bagels left. Thank you. Anyway, this is a pretty simple scheduler. You've seen it before. It's pretty cool. Now we can take a look at the scheduler implementation. First come, first serve. And here, as you see before, we just implement the scheduler interface, as you see here, and then we create the scheduling queue. So essentially, the idea is we have a queue where we push tasks in. And then whenever the CPU is like, hey, whenever a process is like, hey, I'm ready, please enqueue me, thank you, then it calls this method, and what we can then do, we can dispatch it. The cool thing is, with the Java library, we have here, for example, a full Java description, a full Java definitions of all the methods in that I exported from the Linux kernel to eBPF. And we can just dispatch it to our queue and tell it, hey, please, you have a slice of -1, like a slice of essentially infinity, but I was told that everything like above 10 seconds in scheduling is infinity. And you see here, the timeout, if we don't schedule tasks for like 10 seconds, our scheduler will be kicked off and will be like, you're doing some weird stuff, please go away. And it's pretty cool because you can't like fatally stop your system. And then dispatch is also simple. When a process is like, hey, please, can I get, when a CPU is like, please get me a new task, then we just tell like, get one here from the shared TSQ. That's all, and that's a functional scheduler. The cool thing here is this part here is compiled to C, runs in your Linux kernel. This part here, on the other hand, runs in Java. Anyway, should we try it? Cool. It should work now. Now let's run the game. For reference, I think before, so it doesn't change that much because our system is essentially empty. We don't run anything, so what we can do, we can simulate some load because that makes the whole thing more interesting. And I think there is the stress NG. We can just stress our system. And this will get,
yeah, so with, now it's interactive again, but with the first come, first serve scheduler, if we have an interactive system that does I/O and I don't know user interaction, tasks don't run that long just for themselves. If someone didn't place a while true loop somewhere, but the stress ng task that Johannes started just hogs the CPU and just runs basically in a while true loop. So once one task of them is on a CPU, it doesn't get evicted from that CPU and just freezes the system.
But it's not a terrible scheduler because it has advantages. It might sound like, oh, that's a scheduler we never use, but consider this. We know how long a task takes because we have domain knowledge. And when we disable these, we have 0 scheduling overhead because we don't interrupt this. We have no contact. We have no switches between tasks. We have no moving a task from a different CPU to another CPU. It's better for caches. We can even disable some of the events so we can reduce the power consumptions. It's not a terrible scheduler if you know what you do. And the cool thing is, with ScatX, we can explore. And I think that's all for this scheduler. Now we're going on to the... Oh, and by the way, the QR codes that you see lead you to the scheduler implementation.
Yeah, I think we have one more slide about the timeout Johannes showed previously. So that's the reason why the system became responsive again, and that's also one advantage of ScatX. You don't have that in a direct kernel scheduler. The direct kernel scheduler just lets you freeze your system.
And it's real terrible because writing good schedulers is really hard. And there's the first come, first out scheduler. Can you tell me?
That's basically a very similar scheduler to the one we just showed, but now we limit the time slice one task can use. So after a set amount of time, the task just gets stopped, and we decide what task to run next, and with the first in, first out scheduler, we just do round-robin scheduling. And that's also the default behavior of SCADX, so the one that Johannes mentioned a relatively good performance with.
And you have essentially, and this leads us to a dance. So many schedulers have this dance where like processors come in, go into global queue, then they dispatch to a CPU, each CPU has local queue, and then we move them essentially around. They run around the whole system, and that's pretty cool to see. If you see it first time working your own scheduler, it's like, then you never stop, and then you get on stage because you wanted to shout on computers. Anyway, and it's not a bad scheduler. We can show you saw before it froze. It was not great. By the way, I think we're still running stress ng. So eBPF is a pretty good scheduler. We have like 30 FPS instead of like 50. That's fine. Let's start the FIFO
scheduler.
Oh, thank you. The simple scheduler. No, minimal scheduler.
Minimal, yeah.
So the only difference is essentially that that the slice is not -1. Let's see. It's always with live demos. You never know. Okay, you see here that it's slightly worse because, of course, it doesn't. The problem is it doesn't prioritize this. eBPF would prioritize these systems that have short bursts of working. But I think it's pretty usable. It's like a scheduler I can show you. It's like a scheduler that is on the system running on full load because, yeah, it's hocked down, but the scheduler itself is not really big. It's literally the same code.
We are basically doing the same thing, but our slice there is now 5 million divided by the number of tasks queued in the shared dispatch queue. So that's round robin with a slight adjustment for interactivity. So if we have a lot of tasks that want to run, we give the tasks smaller time slices so that the interactive tasks run faster.
And I think the game is still playable. Our system isn't full load. We could have shown you Counter-Strike because I got this idea of showing a game by Andrea Righi. And he's pretty cool. He's a scheduler developer now at NVIDIA. Before he worked at Canonical, and he showed how his own scheduler is far better at compiling the Linux kernel while playing Counter-Strike. So he can still write his and other shooters. So he can still run his shooters and play them while he's compiling because that's a good use of time. Say, why are you gaming? My code is compiling. Okay. Whatever. No, now he's working in NVIDIA and probably it helped him. Anyway, let's stop the scheduler. I think we should have one more scheduler. Let's see. No, stop. So then we have the lottery scheduler. It's a pretty fun scheduler. It's actually one of the first cool scheduler that I learned about at uni. It's essentially, you're the lucky task who gets the time slice. It's essentially like a lottery. And so every task gets a few lottery tickets, depending on the priorities. More tickets means higher priority. We put it into a bowl, and every time a CPU is like, could you get me one? You're like, sure. Randomly draws, and randomly draws is like, I collect the number of tickets that I have, and then I pick a random number and iterate over the queue. And that's a pretty interesting scheduler, as we see in a minute.
Yeah, so we again have probably above the enqueue and dispatch functions.
Yeah. And the enqueue method is as before, but the dispatch is interesting. As I told you before. Yeah.
So here we get the random number with BPF get prandom. So that's a BPF helper function that the kernel provides for us for getting a random number. And we just take that number modulo the number of items in our dispatch queue, and then we with this for loop, we get the task at that index we selected and dispatch it.
Now we're starting. I think we're running out of feedback, out of Q&A time, but I think we still have something left, so you can be interactive here. Anyway, now we have a lottery scalar, and the fun behavior here is the FPS number jumps randomly because there's randomness in the system. How great is this for gaming? You hear the sound, it's like, I think it's pretty cool. I'm not a gamer. I don't know. I heard gamers don't ever talk about latency and the flux of latency distributions. Anyway, I think that's all for these scalars here. There are, of course, more scalars that we could show you, but we only have like an hour left. Oh, an hour slot. So what else can we do? We can have fun, and that's where we're coming here. We can implement good scalars.
Yeah, so as Johannes mentioned with the gaming during compiling, writing our own schedulers might have actual advantages because we can especially design the scheduler for our use case and optimize it for that. We might not want to do it in Java, or you do?
Kernel developers don't like Java. I was at Linux Plumbers last year in Vienna. I was told I was probably the first person talking about Java in decades there. It's like the biggest Linux kernel conference in the world, and I was there with my Hello eBPF talk. But apparently the person that maintains eBPF, he liked the talk as a tool because he thought Hello eBPF was nice for education. Anyway, I know he's not starting writing scalars in Java, but we do. I'm forwarding the knives of Duke. Yeah, the tools were built in different times. You can find more good scalars that work, and even layered that's used by Meta, like they have Facebook, WhatsApp, and so on. They use it all the time in production. Then there's also the idea that you can re-implement scaling and just improve them because you can easily iterate. You can have it, as I showed you before, regarding gaming performance. There's a good talk as this year's FrostM by Andrea Rigi. Anyway, and now we're going on to the experiments because they are fun, and we're alone here in this room, so it's probably fine. One thing that we can do is we can do an erratic scalar. So why should we care about fairness? Why couldn't we just have a scalar that's like, oh, yeah, you can't run for like 200 milliseconds. You not, but you can run like a totally random scalar. That's pretty cool. And that's the chaos scalar. If you want to learn more, you can read about it at LWN. And we'll be giving a specific talk. We gave a talk at FrostM this year that you can also watch. And the cool thing, the basic version is written in Java. Yes! And it's a world-leading scalar. It's the first time someone implemented this in scaling. Yeah. So now we're having fun with SCADX because ensuring fair scalars. This is from a paper like a few years ago, and Jake Hillen from Meta marked this for me and was like, yeah, that's really funny that the person wrote, our reasonable operating system scalars are fair. No, they aren't. Scalars are never fair. Life isn't easy. Anyway.
The one that produces sound is the one we showed at the beginning. Johannes also has one that that reacts to sound.
Yeah. And that's pretty funny. We now start with a simple task because we're here an educational event. There's also Chaos macht Schule and anything. They are pretty cool, but we can do this here too. And so I have a tuning fork. The problem is, if you want to get larger, they are only in esoteric shops and tell you it's the Earth's magnetic sphere rotations. So this is a small one, sorry. It's 440 Hertz, and we're using this in a second. Anyway, let's move on to the scalar. Where do we have onto the scheduler. Let's allow the scheduler. Hope it works. So essentially the idea is that the louder the microphone records it, the faster it gets. So I can show you the numbers going up. I hope you can see it. So it's pretty simple. It's not hard to understand. And now what we need to do, we need to put some stress on our system, of course. The only problem is that when I have to switch tasks, I have to shout at my computer. I can tell you that's really hard. When I tested this code, I think my neighbor probably thought I was crazy. Anyway, now I have to shout, and now we can drive. Let's find our way again. Now the thing is, when we're quiet, funny. When we're quiet, the FPS is low, moving through forest anyway. Can we move back to something else? No, usually. Now it worked. Now it's going back. It's a really cool game. Now it worked again. So the thing is that and now we can try. Can we get it as fast as possible? Now you. Can we get it faster? I'm so sorry for the audio engineers. Please don't hate me. And the problem is that now I have to disable the scheduler. I need to shout. I'm really sorry. Thank you. Anyway, and I think we're running out of time, so I'm seeing this, but there's also a mode where the latency depends on how close you are to the 440 hertz. But I think we're skipping
still
this.
Running, I guess.
Oh, it's still running.
You just
the
stress and G.
Oh, yeah, thank you. That's the problem. These schedulers are so easy to run. You might forget them, and then you're like, why is he shouting at his laptop? Anyway, the cool thing now is, of course, there are the weird schedulers, there are good schedulers, but there are also schedulers that you wrote. Because, may I present you the winner of this year's KIT scheduling contest?
With a lot of competition.
Yes. But he got a T-shirt.
And a mug.
Yes, and a mug because it was the most original idea and the most original implementation. And the only one.
So yeah, I wrote task clicker, and I thought I wanted to design a scheduler for an interactive system. I wanted it relatively simple, so I said I'll write a first come, first serve scheduler. But something went wrong in the implementation, and now the scheduler itself is interactive. And it's not first come, first serve, it's first click, first serve. Can you start it?
Then no.
Yeah. So that's the interface of it. First, we'll have to select some processes we don't want to schedule with our scheduler, because to click we don't want to schedule the system where we click on the task by clicking on the task. That sounds like a deadlock.
That's why we don't use a Bluetooth mouse here.
So we can click start, and then we have all these processes, and we have to click them to schedule them. And you see the syscall balance on the bottom, and that's how many syscalls the task you run have collected. And then you can buy upgrades. The extra arm for your SCADX logo will just get you one more task scheduled per click, and EB will schedule processes automatically for you. So if you buy a lot of EBs, they schedule the whole system for you, and you don't have to click yourself anymore. So yeah, I got it working once to not have to click anything anymore. Yeah, but it's a lot of heavy mouse clicking, and yeah. So we fail after 30 seconds. That's the default timeout in SCADX. So that's your limit you have to avoid with the tasks. Yeah.
So, is here a gamer in there who wants to? We can. I think. Do we have? Okay, we have a few minutes left. Like, do we want to make it a competition? Does anyone want to come? Do we have two people that want to battle against each other in this really cool game? Anyone? We never had one at our presentations. Oh yes, there's someone. Ooh. A round of applause. Let's see how far you can go. And we just need to recompile. Because of course it's written in Java. Why not? You can press start whenever you want, whenever you're ready. Yeah. Yeah. Just like a random process. You can upgrade if you want, but be first. You mean to? Oh, it could supplement my income.
So the syscall balance you have at the bottom is already pretty random. So sometimes you have behavior where you just get one, all of a sudden you get a big burst of syscalls because you just clicked on the right process. And sometimes you have a streak of basically no syscalls for a long time. I
think the idea is that the syscalls are actually the syscalls that are executed by the process that you currently schedule. So this is actually the number of syscalls. So it's not totally random. Oh, he's better than me. You must have been a gamer.
100 of hours in Cookie Clicker.
Oh, yes. Cookie Clicker for the win. Okay, I think we can probably stop this now. I think you will probably finish. Oh, should we do this besides the talk? We've been doing this talk for a couple of times and nobody ever come on stage. Thank you again. I don't know, why are people so shy to show a good they click? The rumbling again. So, it's essentially the first idle game skill. Yay, it's the first in the world. Nobody ever did it. I don't know why. Do you know why nobody ever did it? I think one of the ideas, because
the idea was pretty obvious to me. So,
and it wasn't possible before, because before, when you had to modify the Linux kernel, nobody would do this just for a stupid standard talk.
And especially eBPF provides very easy interaction with the user space part. So for the UI, we have very easy communication with the scheduler part. That's also a big point of SCADX.
And eBPF, and hello eBPF. I think that's all. If you want to learn more about David, go here. He's just a student at KIT. Yay! He's just starting out with writing skills. I'm Johannes Bechberger. I work on OpenJK at SAP. And if you want to learn more about the whole library, you can find it here. And now on to your questions. I think we still have a few minutes left. And please don't ask the question why we do this in Java. Because when I was at Linux Plumbers, someone asked me, I thought it was a joke. Please don't. That's harmful.
Okay, David. So yeah, in fact, are any questions to this talk in the audience? Okay, I come.
Yeah, thank you. With fairly good understanding how eBPF works and how schedulers works, I have still somewhat a naive question about the API. How would you tell, or which syscall, eBPF syscall would you use to tell your operating system, which brings its own scheduler inside the kernel, like the Linux system you're running, to, hey, take this one from the eBPF. Is there like a syscall where you tell, turn off your kernel, and it's all right?
I think it's a special kind of eBPF map. They can provide some structs, and if you use the scatx struct, it just replaces the scheduler. But a lot of the low-level stuff is handled also with eBPF, is basically a Java API for libbpf. So a lot of stuff is handled by that.
Okay, and when you exit, you do the turnaround kind of.
Yes.
Yep.
Perfect. Thank you very much.
Okay, I must say I have a question. Talking about the deep level stuff, is like I hear your scheduler is messing around with my kernel. Can you talk me out of security concerns?
So all your code is verified by the all the code is verified by the eBPF verifier. So that's a part of the kernel, and if you trust that, you hopefully trust that our code that passed the verifier isn't malicious. But of course, loading code into the kernel is always a bit
Please kids here, don't put any random USB thumb drive into your computer and expect everything will be good. And please don't leave your system open at GPN. In the end, you have NixOS installed. So it's the same. It's the same. Yeah, you're laughing now. Anyway, no, the main issue is here, of course, you're doing low-level stuff. It has root privileges. It needs root privileges. Please, 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 only get it from proper vendors, from people you trust. Please, don't download random code from the internet and just run it. That's called programming, not systems development. Sorry for the Stack Overflow joke. Anyway, more questions here.
Okay.
So, I'm sure you guys know that AI is all the hype now. Have you guys considered combining AI plus the scheduler?
So there are already, so that's not my work, but Andrea Rigi, who is one of the main developers in the SCADX ecosystem, he asked the AI, hey, please, here's an API, userland API in Rust. Can you write me a scheduler with these properties? And it's kind of good, but also kind of scary because it made mistakes. But we thought about this. The main issue with scheduling is just the latency. If your scheduler takes 1% of your work time, that's not really good. What you can do is you can pre-compute, you can use AI to analyze the behavior of your process, and maybe in the future schedulers will do, to automatically select the best scheduler for your system or to select the properties or such. But the main scheduler, the low-level stuff, please don't do it. It's similar to what you do in firewalls or such, where you essentially have like your low-level dispatching, that's handled by SCADX in the kernel, that's fine, or by your firewall, and then you have the above level where people use AI to do more analysis.
Yeah, for the big picture stuff, that's definitely in the mind of some people. I think at Meta, where some of the SCADX originated, if I remember correctly, in the patch set for the initial SCADX patch set, there is already they already talk about using AI models for a bit of the bigger picture stuff of optimizing your schedulers.
All right, any more questions, please? No, I think we are through. Then again, a big applause for Daniel and Johannes.